Welcome back to the Chem OG. Today we're going to take a look at cell potential in an electrochemical cell. And what cell potential does is it measures the favorability of an electrochemical reaction. So we're going to take a look at a reaction in which electrons flow around, a redox reaction, and we're going to examine whether it's favorable or not by taking a look at the cell voltage. And so the cell voltage is calculated as the reduction potential plus the oxidation potential. So these are values that you can look up in a reduction table, and whatever is going through the oxidation, make sure to flip that reaction, as we spoke about in a previous video. And so when the cell potential overall is positive, it means that you're looking at a cell that can happen on its own, or what we call a galvanic cell. Sometimes we call it a voltaic cell, and in particular applications, it can go by other names as well. If this cell on its own cannot operate because it would require a non-spontaneous reaction to happen, you have to hook it up to a battery or some sort of electromotive force. That's known as an electrolytic cell. So this kind of reaction would be unfavorable on its own. Now, if your cell voltage overall happens to be 0, that means your reduction and your oxidation kind of cancel out together. What that means is that you're not going to have any current flow because there's no push towards going to one side or the other. That means that you're not going to have any current flow at all if your cell potential is 0. So our discussion just a moment ago about favorability or lack of favorability should immediately make you think of delta G. So is delta G related to the cell voltage? And the answer is absolutely yes. Delta G is related to the cell voltage, but they're opposite in sign though, as you may have noticed. So when you have a favorable reaction, its cell voltage is positive, but the delta G for a favorable reaction is negative. So there's going to be a negative sign between delta G and between the cell voltage, and that negative sign is right there. The two other variables here are N and F. N is the number of moles of electrons transferred, and I'll show you how to spot that. And F is Faraday's constant, and it's sort of a proportionality constant that relates delta G to the cell voltage. And so we need to be able to relate the charge that's carried by a mole of electrons. So a mole of electrons carries about 100,000 coulombs worth of charge. Now, if we take a look at an example redox reaction, in the balanced reaction here, 2 aluminums react with 3 iron ions to produce the products. Now, in order for 1 unit of this reaction to occur, each of these aluminum became aluminum 3+. So when 2 of them get oxidized, that means they gave up 6 electrons. So N would be 6 in this case. Notice that you can also figure out that N is 6 by looking at the iron instead. So I have iron 2+ became iron, and so each one of those requires 2 electrons, and there were 3 instances of iron taking on 2 electrons, so 6 electrons got gobbled up by the iron. So since we are talking about delta G, let's bring back a good old equation. And that was the one that we talked about previously, in which we related delta G for a reaction to the standard condition delta G. And we said that delta G equals delta G naught plus RT natural log of Q. Now that we can relate delta G to the cell voltage, what I'm going to do is I'm going to substitute in, whenever I see delta G, I'm going to substitute in negative NFE that we just talked about. So if we're looking at the current cell voltage, and this is, it's supposed to say cell, but a lot of times we can drop it. On the left-hand side, we have negative NFE, and on the right-hand side, because we're looking at standard conditions delta G, we need to also take a look at standard conditions voltage as well, and the rest of the equation kind of stays as is. So to kind of simplify things a little bit, what I'm going to do is I'm going to divide both sides by negative NF. Okay, so I'm going to divide both sides by negative NF, and that's going to drop the NF from both of these terms, but it'll leave the NF at the bottom here for this term in particular. So now we have a way by which we can take a look at the current, whatever the cell voltage is right now, by being able to take a look at the standard voltage. So the standard voltage is something as a reference value that you can look up. If you want to figure out the voltage under the available conditions that you have, look up the standard voltage for the reaction that you're undergoing, plug in the temperature at which you're operating, and this temperature needs to be in Kelvin. Use the appropriate universal gas constant value. You already know how to take a look at the number of electrons that are transferred. We already talked about the value for F. And so what you would need to do is you would need to compare the ratio of products to reactants at that point, and that'll give you the cell voltage. So what we took a look at was something called the Nernst equation. The Nernst equation is very, very important. What we want to do now is we want to take a look at a very particular scenario for the Nernst equation. And the scenario that I want to take a look at is what happens at equilibrium. So remember we said that when we're at equilibrium, delta G is 0. Well, when we're at equilibrium in terms of an electrochemical cell, it means that there's no current flowing because there's no reason for it to. And so that means that the cell voltage is going to be 0. And if we are at equilibrium, it also means that the value of Q is going to be equal to K. So if I substitute in both these values, whenever I see the cell voltage, I'm going to plug in 0. And whenever I see Q, I'm going to plug in K. That's going to give me that E naught, which is the standard voltage, which is not necessarily the one at equilibrium, that the standard voltage, the one that's taken at 25 degrees Celsius, it's the one that's taken at 1 atm of pressure, and it's the one that's taken when all of our concentrations are 1 molar. That standard voltage is equal to RT over NF times the natural log of the equilibrium constant. To give you a summary of all the equations that we learned today, here's what we got. We learned that delta G equals negative NFE, and so that way we can relate the cell voltage to the delta G for a reaction. We also learned that if you want to find out the cell voltage for a reaction, another way to do it is to start from the standard voltage and figure out what your product to reactant concentration is at that point, and plug in for the gas constant, the temperature, and the number of moles of electrons transferred, and put in Faraday's constant as well. When we're at equilibrium, well, the E value becomes 0 and Q is equal to K, and so that means that E naught equals RT over NF, natural log of K. The other thing that we can do is we can figure out the equilibrium constant from the standard cell voltage if we rearrange this equation. So what we can do is we can multiply both sides by NF, so that'll give us NFE, divide both sides by RT, essentially take this fraction over here and put it as the reciprocal on the other side of the equal sign, and then we can take the natural exponent of both sides, and that'll give us this equation, and that is that the equilibrium constant is equal to e to the power of NFE naught over RT. Thank you so much for watching today's video. Please make sure to hit the like button and help support this channel by subscribing to it. See you at the next one.